what we want to understand is that we can infer genotypes based on patterns of inheritance, essentially looking at a pedigree. And that's what we have here in our Jack and Jill story. I'm not going to go too much into the story. I just want to talk about different patterns of inheritance here. So freckles is a trait that is going to be a traditional dominant recessive trait. It's not sex-linked, so we call it autosomal. That just means not a sex chromosome is where this gene is found, any of the other 22. Freckles, in this case, right, we find that Irma and Donald both have freckles. Okay. Their son doesn't. Well, if this was a recessive trait, that would mean Irma and Donald would have to have only recessive alleles. There's no way they could both have only recessive alleles and produce a child that doesn't then have freckles. So that tells us, just by looking at that pattern, that there's no way that freckles is a recessive condition. It must be dominant. And because it's dominant, then Irma and Donald can be heterozygous. They can have one big F, one little f, one big F, one little f. If that were the case, right, then we would do our Punnett square, and we would end up having a 25% chance of them having an offspring that that would not have freckles like Jack. So that tells us what their genotypes have to be because of the pedigree chart, right? The pedigree that they have. Blood type is an unusual pattern of inheritance, and that this is showing us that cross that we would have done. That's the only way Donald and Daisy could work. Blood type is a different pattern of inheritance. There are two things about blood type that are different. First, it doesn't just have dominant and recessive like we've been talking about the last few weeks. Instead, it has an A allele, a B allele, and an O allele. An A allele gives you a certain type of antigen sticking off of the blood cell. A B antigen gives you a different kind of protein sticking off of the cell membrane of the blood cell. And an O antigen, an O allele, gives you no antigen sticking off. So those are our 3 alleles instead of just 2. We call that multiple allelism. We also, in this case, see what we call codominance. And we call it codominance because if an individual were to end up with a genotype that is AB, you would end up having a blood cell that's phenotype is having both the A protein and the B protein sticking off of there. They both show up equally. So that's what gives us that AB phenotype, is having the AB allele, that codominance, rather than traditional dominance, which when one shows up, it dominates over the other. Now, both A and B, you see A in the lowercase I represents the O allele. Both A and B are dominant to O. So if you have A and O alleles, you end up with the A phenotype. If you have B and O alleles, you end up with the B phenotype. The only way you get the O phenotype is if you have your homozygous recessive for the O alleles. So that is codominance. And blood type is the greatest example of that. It's nice and clean for us. One thing that students sometimes struggle with is when we start to introduce this idea of Rh factors. They want to include that as being the same thing as the ABO allele. The ABO allele is a completely separate gene. You could think of this as eye color and chin dimple. Okay. The only reason why we tie them together is they're both related to our blood, but they're 2 completely separate genes. And in this case, positive is dominant and negative is recessive, because positive means you end up with a different kind of protein on there, and negative means you don't have that. And so that's where the concept of this is often mistaken by students. You need to treat these as 2 separate genes, meaning if I had an individual who was AO and an individual who was, and that same individual was positive negative, I would have to put that positive allele in a Punnett square with both the A and the O, the negative allele with both the A and the O. So I'd end up having at least 4 possible gametes from that particular individual. So that's something you want to make sure you don't mistake, right? That these are 2 separate genes. So we have to do dihybrid crosses with them. So if we were trying to infer genotypes here, right? Irma has type A blood, Donald has type B blood. So we know Irma has at least one A allele, Donald has at least one B allele. We don't know what their second allele is until we look at Jack and see that Jack is O. The only way Jack could be O is to get a lowercase I, 2 O alleles, homozygous recessive. Well, if he's homozygous recessive, he had to have gotten one of those from each parent to get to 2. And that means Irma, who is A, so she has to have an A allele, also has an O allele, so she has to be heterozygous. And Donald also had to be able to give Jack one of those. So Donald has to have a B allele, which gives him his phenotype, but also an O allele he could give to Jack. And so that helps us determine the genotypes of these individuals. It just takes practice and thinking through, what does it mean? What does it mean when I look at this pattern of inheritance described here, okay? Similarly, we talk about Rh factor. I mentioned that positive is dominant to negative. Both of these individuals are positive, which means they would both have the positive allele, but only need one to have that. They have a child that's recessive, so that means both of them would be heterozygous for the Rh allele. And then when we do that Punnett square, we have to do all of these out, right? We have to have all these possible combinations. So here's a nice example of that filled in for us, okay? Now we don't know Daisy's second allele in this case. And so it's just represented by a question mark. But that, hopefully that made sense as they're going through that why, what we were trying to rule in and rule out, right? Essentially, we're saying, could they produce a child who is O positive like Jill? And so that's why we just needed to, we didn't know what Daisy's second allele was for blood type. We couldn't rule it out because we didn't have enough information, but we could use what we had to see if we could produce a child who was O positive at least, right? And there's at least a chance, right? Because all 3 of these would be O positive, which is what Jill could be or is, right? So a definite possibility there. All right. So those are the next few patterns: codominance, multiple allelism, and then just dominant and recessive. Those are the first 3.